It's a pleasure to introduce our next speaker, Professor Nader Masmoudi from Quran Institute, and he will be talking about the Euler mechanism for the two-dimensional Euler dynamics.
Okay, so thank you very much for the introduction, and thank you for being here. Okay, so let me start by maybe saying a few words about what I think are important issues in fluid dynamics, and especially studying the dynamic of flows. So I put a question about stability, long-time dynamic, transition from laminar to turbulent flows, inviscid limit. And I mean, this is an area where there is an interplay between analysis, numerics, and experiments. So I think we saw this kind of pictures before, but this is a picture about the flow. I mean, like here, this point is so-called like separation point, and this is the type of things we see where we have transition between laminar and turbulent. I like also this kind of picture which shows the stability of vortices. This is a picture that shows transition between a laminar flow. So here you have a laminar flow, then you have something happening, and then it becomes turbulent. This is a picture, I mean, this is a slide about a very known experiment done by Reynolds in 1883, where he looked at a flow in a pipe when the Reynolds number changes, when you are making a bigger and bigger Reynolds number. So when the viscosity, which is like the inverse of the Reynolds number, when the viscosity is large enough, you see a laminar flow. But then when the viscosity gets smaller, you start seeing transition to turbulence, and that can happen earlier and earlier. So my talk, I will first revisit this Reynolds experiment. Then I will try to explain something about the 3D, which is the so-called transition threshold, and I will discuss few results, but then I will focus on the inviscid 2D case. So today I will not talk about 3D Navier-Stokes, but I will be talking about 2D Euler. I decided to choose one result to illustrate what we are doing in this area. Okay. Okay, so this is again the same slide about the Reynolds pipe flow. So as I explained, what Reynolds was observing is that when the Reynolds number is getting larger, we are seeing transition to turbulence. However, this poses a small problem, because if one looks at the linearized Navier-Stokes around this laminar equilibrium, then this linearized problem appears to be stable for all Reynolds number. So, so it means that something is happening that's not just explained from the linearized problem. Okay, so how do we want, I mean, we want to give some explanation to this, we want to give some more precise explanation to this problem, which, by the way, in the physics literature is sometimes described as the Sommerfeld paradox. So we will start with the 3D Navier-Stokes. So V is the velocity, P is the pressure, Reynolds -1, this is like the viscosity, and we have the divergence-free condition. So since this experiment by Reynolds instability at low Reynolds number than what is predicted by linear theory has been observed in many laminar equilibrium. So it's not only the pipe flow. And today I will try to explain this with the simplest flow, which is the Couette flow. So the 3D Couette flow is the following flow. So maybe the next transparency it's better. So it's a flow which is equal to, oh, I didn't write it down, please. Okay. So it's equal to y 0, 0. So it's y in the x direction and 0, 0 in the y and z direction. So this is so-called shear flow, and this turns out to be a solution of the Navier-Stokes equation for all viscosities. And we'll look at this in the case where x will be in the torus, y will be in the whole space, and z will also be in the torus. So a natural question to ask is whether this flow is stable, right? So what you do then is you write down your solution as this particular stationary solution plus the small perturbation, and then you write down an equation on the perturbation. And then you ask yourself, if I choose u to be small, in a sense to be precise, can I prove global existence? Can I prove that the solution I can prove globally, and then can I keep u to be small? So it turns out that a way of also resolving this Sommerfeld paradox that I mentioned is to look for so-called transition threshold. So you fix a norm x. The norm x can be L2, can be Sobolev, can be analytic regularity, so it can be many different things. And then you are looking for a gamma, some constant that depends on your norm, such that if your initial data is much smaller than the Reynolds to the power minus gamma, you have stability, whereas if you are larger, then you can get some possible instability. Okay, so by the way, this will give somehow an explanation to the problem that Reynolds was encountering here, because what it can tell you that if gamma is larger than 0, it means that when the Reynolds number is getting smaller and smaller, the size of your perturbation has to be smaller and smaller. So then this can explain why we have that transition to turbulence. Okay, so this is more or less the question we want to address. And I mean, this kind of question was studied both at experiment, numerically, and only very recently we have some mathematical analysis about this question. Another thing is that it's not obvious from the beginning whether this gamma should depend on x or not. But a priori it may depend on x. There's no reason to assume that the gamma doesn't depend on x. Okay. Okay, so let me first talk about some existing work. So there are experiments, different experiments that somehow suggest the value of gamma like 1. There are numerics. Turns out, like for numerics, people have distinguished two types of perturbations. So they distinguish perturbations so-called smooth and rough. The way, like if we want to translate this mathematically, the smooth perturbation refer to things like analytic perturbations, whereas rough perturbation are more like Sobolev type perturbations. So the type of values that are observed are like gamma equal 1 or gamma equal, let's say, 3/2, depending on the regularity you are imposing. Okay, so there are also papers about formal asymptotics. I mean, there's a paper suggesting also gamma equal 1. Now, from mathematic, and rigorous works, I think the only paper we're aware of was a paper of Romanov from the 70s where he computed like a value of gamma like around 4, which means like very small initial data. I mean, the proof here is straightforward energy estimates. Okay, so let me now describe some of our contributions on this area. So the type of norm we are considering are so-called Gevrey norms. So these are norms which are between C infinity and analytic. When you have an analytic function, the Fourier transform decays like exponential minus xc, whereas here for Gevrey norm, your Fourier transform will decay like exponential minus xc to the power s. So basically, you take your Fourier transform, you multiply it by exponential lambda xc to the s, and you square the whole thing, and you require that this is finite. When s is equal 1, this will correspond exactly to the analytic case. So the first result here is to say that if you take this norm and you take an initial data like Reynolds to the -1, so like your initial data is same size as the viscosity. Of course, here there is a small constant here. Then you don't have transition to turbulence, meaning that we can prove global existence and stability. So this was the first result with Jacob and Pierre. And on the other hand, if our initial data in this same norm is larger than the viscosity, then we can prove some sort of instability, meaning that we can prove that our solution starts as small as you want and then grows till it becomes of size 1. For this result, we need the initial data to be between the viscosity and the viscosity to the power 2/3. One reason about that is that you want to control this instability. So you don't want your initial data to be large, because if your initial data is too large, then some other nonlinear effect can happen and destroy this instability that you are looking for. So this is the result in the Gevrey regularity, and then we have another result in the Sobolev regularity that suggests the value gamma equal 3/2, meaning that we can prove that if our initial data is less than the viscosity to the power 3/2, then we have stability. Here, when we are measuring the perturbation in Sobolev regularity. Okay? So more or less these two values of gamma, 1 and the 3/2, they more or less match the values that are observed numerically and experimentally in the previous results I mentioned. Okay. So today I'm not going to talk about ABC, but I'm going to talk about the 2D case. So in the 2D case, we have similar results. It turns out that we are using the same norm, but for completely different reasons. So the reason we use here this same Gevrey norm is very different from the reason we use Gevrey in 3D. And here we have a result that says that actually gamma is equal to 0 in the 2D case, meaning that I can take perturbations which are independent of the viscosity. So this was a result with Jacob and Vlad, which came after a previous result that I had with Jacob that treated the 2D the 2D Euler case. Okay. The last result is about the optimality of the Gevrey regularity. Okay, so this is the reason I chose to really discuss these two results, is that after this first work, we had always the same question whether the Gevrey regularity is really necessary or not. So it was important that we try to prove the optimality of this Gevrey regularity, and this was a result, recent result I have with Yu Deng, where we prove that if one takes this Gevrey regularity but with S less than 1/2. So here in the previous in this result we need S to be bigger than 1/2. So with Yu Deng we prove that if S is less than 1/2, then we have instability, meaning that you can take your initial data as small as you want, you will become large. So somehow this proves that the Gevrey regularity is the right regularity to measure the perturbations. Let me here just mention one thing, as you'll see in the proof. I mean, there are many results that one can prove about instabilities, and where sometimes we see that you need some sort of regularity. For instance, like if one thinks about Kelvin-Helmholtz instability, Rayleigh-Taylor instability, or instabilities in the Prandtl system, all these equations, we can see that there is some instability and it will require maybe some sort of analytic or Gevrey regularity. But in all these cases, the requirement is coming from the linear analysis. So when you do your linear analysis, you see that you need a sort of regularity. In this case, the requirement about the Gevrey regularity is not coming from a linear analysis, but more from a nonlinear analysis. So this is the interesting feature of this question. Okay. So recently there were a lot of works that came after dealing with this question about so-called inviscid damping, meaning what happens when you linearize Euler, but around different flows, not necessarily the Couette flow. Also the notion of enhanced dissipation when we put viscosity. So all these are recent works about inviscid damping. What happens when you linearize, but not around Couette, but the vortex? That was one of the pictures I showed at the beginning. So we have these other works about enhanced dissipation, other models. Let me also mention that all this is also related to the so-called Landau damping in the Vlasov-Poisson. So there is a nice similarity between the two problems. turns out that the Euler problem is slightly more difficult because we have much less decay than in the Landau damping problem. Okay, so let me now start discussing the 2D case. So let's forget about Navier-Stokes, forget about the 3D, and forget about viscosity. So all I want to explain is in the 2D case and explain the requirement about Gevrey. Where does this requirement about Gevrey come from? And why is this regularity critical? Okay, so you start from the 2D Euler. So we are in 2 dimensions. I'm taking x to be in the torus, y to be in the whole space. So this is the 2D Euler. You can also write it in vorticity form, like this. And for 2D Euler, any function, if you take just, I should put u1 here, but if u is just, if the first component is just a function of y, this will be called a shear flow, and all these are stationary solution of 2D Euler. If you want to be also a stationary solution of Navier-Stokes, then that will require u of y to be like linear, to be affine. So that's why you only get that Couette flow. But here you have any function like this of y will be a stationary solution of 2D Euler. The case u of y equal y, that's the Couette flow, and that corresponds to a vorticity which is like a constant. Okay, so now we want to perturb around this. And now if I perturb around it, so I'm thinking now about my vorticity as being -1 plus omega. So if my vorticity is -1 plus omega, then this is the new equation satisfied by omega. So omega now is not the vorticity, but is the perturbation. Right, so it satisfies the same equation, but with this extra linear term. So this equation is actually linearly stable. I mean, there are no growing modes. However, again, like I'm back to that Sommerfeld paradox, it suggests that there may be some strong nonlinear effects, and that's what we want to explain here. Okay. Okay, so let me reintroduce the Gevrey norm. So this is the norms I mentioned. Here I'm looking at these norms in 2 dimensions. Remember that x was in the torus, y was in the whole space. So then when you take the Fourier transform, x will be, k will be in z, and c will be in the whole space. So this is your Gevrey norm. It turns out, I mean, this is a very nice exercise, is that this characterization on the Fourier side, there is a similar characterization on the physical side that measures the growth of successive derivatives. So this definition is actually equivalent to the fact that if you take your f and you take alpha derivatives, then alpha derivative will grow like this. Will grow like this factorial. Yeah, I mean, you can see when s equal 1, you recover the, when s equal 1, you recover the analytic regularity. Okay. So then the first result, again, this was the result I mentioned with Bedrosian. Okay, it appeared 2015, but I mean, it was completed before. It says that if I take my initial data small in the Gevrey regularity, I mean, we need some small lava decay when y goes to infinity, but this is the major assumption we make. If we take our initial data in this space, then after some change of variable, so I cannot keep omega in the same regularity because, I mean, there is this sort of mixing due to the ydx term, so I need to make a change of variable. So after making some change of variable, we can prove that omega stays bounded in a similar Gevrey space. All what we are losing is a little bit on the lambda. So the power lambda, which you see here, will decay a little bit. I mean, this is inevitable whenever you have results in analytic regularity. This is always the case. Like whenever we have a result in analytic regularity, this is very, very standard. Like if one thinks about Cauchy-Kovalevsky type of result, there is always a small loss on the radius of analyticity. So this is very similar to that. So basically, okay, you take data which is small in this Gevrey regularity, and then you can prove that globally in time, you stay in that same space after you make this change of variable. Actually, our result has another part to it, which is asymptotic stability, meaning that our omega will converge to a new f infinity, which depends on x omega. Again, after you make this change of variable. So what this means that you start with an initial data which is close to Couette, but then we have to converge to okay, sorry. We are converging actually to a flow. This is our new flow. So this psi of W is like W plus a small perturbation. Psi of Y is like Y plus a small perturbation. Okay. Now, the next result is the result with Udang, where we prove that if now S is less than 1/2, then we can take an initial data which is small in that same Gevrey space, but which becomes large in some Sobolev norm at some time t. Okay? So clearly this shows that in the stability result, the Gevrey regularity was necessary. Okay. And actually, I mean, what that result shows that there is no possible choice of change of variable. There's no way you can make a change of variable so that this stays small. So for any phi, this will be large. Okay. I mean, here there's a remark that we can even be more. I mean, we can replace the S less than 1/2 by some log correction of the G 1/2. Also here there is a small remark on the time needed for this to happen. Okay, so let me try to give an idea about the proof. Okay, so before that, I mean, these are also related works, both on the Couette flow and on the Vlasov case. I mean, maybe this is more related, where Jacob, he also proved similar result of non-Landau damping in Sobolev spaces. Okay, so let me try to describe few ideas about the proof. So I will try to describe a little bit the idea about the proof of the stability result, and then explain how we can use some of those ingredients in the instability result. I will only focus on one part of the proof. I mean, the proof has many other technicalities that I will not discuss. So if one linearizes the vorticity equation, this is what you get. You get a simple transport equation that what you can solve. Okay, and this explains that sort of change of variable that I mentioned. I mentioned like in the result, I don't want to go back, but I had that sort of small change of variable. That's the change of variable is a nonlinear version of this change of variable here. So then one can define, instead of using this variable, I make the change of variable I will call f of tzy to be this omega. Then if one goes back to the nonlinear equation, the nonlinear equation will look like this. Okay, so all I did is I'm getting rid of okay, no, sorry. I think it will come later. Yeah. I'm just getting, I mean, I don't want to go back because I'm getting rid of this transport term in the equation of omega. So this is what now you get. Let me, before studying the nonlinear problem, let me show you something about this linear thing, the linear equation. So if one looks at the stream function, so the stream function is the Laplacian minus 1, the stream function phi is the Laplacian minus 1 of f, but it turns out that when you make the change of variable, the Laplacian minus 1 becomes this Laplacian minus 1. Okay, so you have, and it's just calculus, it's very simple. Think about change of variables. This is your new stream function, and this is the new way of recovering the velocity. So you have this Laplacian minus 1. So the point here is that even though omega is just transported, so omega will not decay, but if you go to the stream function, which is the Laplacian minus 1, the stream function will decay, and also the velocity will decay. So basically, this is what you can read on the stream function. You look at Laplacian minus 1, and you get the following thing, like you take f and then you multiply it by this. Now the point about this is that when t goes to infinity, this will behave like 1 over t squared. This will behave like 1 over t squared, so you expect this to decay like, the stream function you expect it to decay like 1 over t squared, and also you expect the velocity to decay like 1 over t. And actually, this is really the starting point of the idea about inviscid damping. And this was already observed by Orr in 1907. So he already observed that when you do this change of variable, when you solve omega due to that mixing, the stream function will decay. So this is actually a picture, like if I choose eta much larger than eta and k that have the same sign. Okay, so maybe I need to talk about the transparencies that you see, unfortunately. But okay, so let me say a few things about the previous thing. Okay, so here what you see is the fact that this decay actually will, it's good because things will decay, but they can grow before decaying. I think if you look at the function 1 over 1 plus x squared, if you look at the function 1 over 1 plus x squared, it's like it goes up and down. And this is basically what can happen when with this, like, you can see that I told you that phi will decay, but it can grow before decaying. And actually, this sort of picture shows it. Like, you can have something which is unmixed. You have something which is mixed, so then it unmixes, and then it mixes again. So basically, the picture in the middle is a picture where you can see growth before seeing decay afterwards. The growth here comes from looking at what happened when t equals xc over k. So when t is equal to xc over k, that's where your denominator becomes maximum. So you can start with a function which may be small, it will grow, and then decay. So that sort of thing that you see on the Fourier side, you can also understand it on the physical side by this kind of pictures. And okay, these are experiments that show that, I mean, it's not very easy to understand, but somehow you can start with an initial data that has two modes. The two modes will decay, but then there is some sort of nonlinear effect that you see much later, coming exactly from those transient growth in the OR mechanism. Maybe I will not try to discuss this. So now, the transport, if one wants to look at the nonlinear problem, and you have to understand the nonlinear term. So it turns out that the nonlinear term will have a part which comes from so-called transport. This will be harmless because we expect the velocity to decay after this change of variable to decay at least like t minus 2. So I will mostly concentrate on the other part, which is so-called reaction. I mean, the reaction term is a term that we define based on a paraproduct decomposition. So we look at frequencies where phi has higher frequencies than f. So that corresponds here to the case where L and eta, where L is very close to k and eta very close to xc. So you take this, you apply, this will give you the gradient of phi. So this is the term that we call reaction term. So then in the nonlinear problem we try to come out with a toy model that mimics the growth due to nonlinear term and especially due to the reaction term. So this was the first toy model that we had in the stability result that mimics the growth that comes from this equation. Okay, I have to think more about. Okay, anyway, so here, let me move fast because maybe of time. We end up actually with a model, with an ODE model that mimics the growth. So roughly speaking, this model controls how those transient growth can interact with the nonlinear term, and then you want to look at what is the growth that you get ultimately. So it turns out that if you look at this ODE, you look at this system of ODE, you think about xc as being fixed, and you look at this system of ODE and you try to see how growth can come. So growth comes exactly when this is 0. So when time is like C over L. So then you look at, you fix C, but you look at all system, and whenever, on different time intervals, you look at which one of the frequency become resonant, and that frequency that become resonant can talk to other frequencies, and that's how you can get growth. So let me go fast on this. This is the kind of growth that you expect at around that time Tm. So in this kind of interval, you expect to see growth of this size. So then you put all these growths together, and if you put all those growths together, that's how you get exponential of square root of xi. So it's really, you are looking at what happens when frequency m talk to frequency m minus 1, talk to frequency m minus 2, and then you look at all the possible growth, and then you multiply them together, and you end up with that factor. Okay, so this was one of the main things in the stability result with the Jacob-Bedrosian. Now, in the instability result, we have to make sure that I can find an initial data such that that sort of growth that I mentioned really takes place. So now the difficulty is the fact that the growth that I mentioned here is like more like an envelope. It's like the worst case scenario. So I need to make sure that I can construct an example that does that worst case scenario. Another thing about it is that, okay, here I had two toy models, one which was of an ODE type, and one which was more accurate. So this is the ODE. The ODE model is the one that was used to guess this exponential square root of xi, but now I need to work on this more accurate model. So then we are able to do that. Okay, so first we fix a background. This will be the frequency that have only k equal plus or minus 1. And we try to use that to allow information to move from k to k minus 1. First, we have to make sure that on each one of these intervals, there's almost one phenomenon happening, and all the rest can be controlled. All the rest can be small. So that's the first estimate that we have to do. Then the next thing is to really prove that when the mode M is so-called resonant, this is mostly what happens. The mode M will talk to mode M minus 1 and mode M plus 1. So then we are able really to make sure that this happens, more or less. I mean, we need to estimate errors, so there are a lot of errors to be estimated. So one thing about this more accurate model is that we keep some sort of convolution on the Fourier side. So there's a convolution that stays on the Fourier side. Then we go back to the physical side, it becomes product. So basically this is what we have. Like we have the mode M talking to the mode M minus 1 by multiplication by this factor. One new thing that we need to do in the instability result is to make sure that this factor is larger than 1. So, I mean, it's not difficult to see that if you start doing these kind of things, you have to make sure that the support of this function stays where this is large. So you don't want the support of this function to spread. So clearly we need to propagate some localization in the y variable, which was not necessary in the stability result. So here we had to propagate some weighted norm in the y variable to make sure that our perturbation stays well localized also in y. So this, let me skip this. So this comes with a bound of this nature that we had to propagate also. I can get like 1 more minute, 2 more minutes maybe. Okay. So okay, so let me now go through the steps of the proof of this instability result. So first of all, we choose a background. This was what I called the frequency the frequency +1 and -1. So somehow you don't look at, you are not perturbing Couette, but you take Couette plus something which is, let's say, analytic, which does the right thing, but you perturb this solution with some Gevrey with S less than 1/2. So then we choose C0 very large, M0 very large. M0 will be like an integer, and the time. And we choose a perturbation of size epsilon prime very small. And then we can make sure that between time t0 and 2t0, if we go through this sort of more precise toy model, I can make sure that there is a growth from this size epsilon prime to some size C0 minus 10. So this growth is what allows me to say that my solution grow from Gevrey regularity to some Sobolev regularity. So basically here, if you calculate this in some high Sobolev norm, it will be large. Whereas it was small in Gevrey regularity at time t0. So then we have to go back to time 0. We have to make sure that the evolution between time 0 and between t0 and 0 doesn't really grow the Gevrey norm. So that's more or less like the argument I had with Jacob. So somehow this keeps really the size. At time t0 we are small in Gevrey, but also at time 0 we are small in Gevrey. And then we have to control other nonlinear terms, and then we have to translate this into the estimate for omega. Okay, maybe I don't have time to go further, but let me say some further questions. So there are questions about asymptotic instability. Can we, I mean, here our result says that between some time t0, between time 0 and time 2t0, you have growth, but then we don't know what happens afterwards. Can we prove that? Can we find an example where when t goes to infinity, this goes to plus infinity? This is much more difficult question than the one we have. Another question is whether this instability is generic or not. I mean, we expect this to happen all the time, but as of now, we have just one example that does this. Okay, so I think this is the end. I wanted at the end to tell you about this new journal, the Tunisian Journal of Math, which is like a general journal. And so if you have some good papers, send it to this journal. Okay, thank you.
Any question? No question? Comment?
Any comment on the two-dimensional Navier-Stokes for the counterexample?
Yeah, so the 2D Navier-Stokes, that was okay. I mentioned this in the 2D Navier-Stokes it works also. Okay, so it depends what's your question exactly about the 2D Navier-Stokes, but in here, so after the work I had with Jacob, we had also a work with Vlad, where we proved that you can put viscosity. The viscosity doesn't destroy this phenomenon. But I mean, we are not really using the viscosity to help us. Yeah, so then there is another result that they have that right here. So in Sobolev, this is a result of Jacob with Bekol and Wong, where they prove that in Sobolev regularity, gamma is like 1/2. So if you take 2D Navier-Stokes with Sobolev regularity, you can allow perturbations to be of size the viscosity to the 1/2. But this is very soft analysis, doesn't require, it's a short paper, doesn't require a lot of...
Can you prove some instability then?
As of now, we don't have those kind of instabilities. Yeah. Like, I can tell you why I need Gevrey in the Inviscid case with this paper, but why we need Gevrey in this paper also, in this result, I can tell you why we need Gevrey, basically, because this is, even here, I mean, I will say we are not 100% sure we know why we need Gevrey, because this result with Sobolev regularity is still not optimal. So the Gevrey requirement in the Navier-Stokes case, as of now, I cannot tell you why we really need it. I mean, it comes from toy models similar to the one I showed you for Euler, but still we cannot prove why we really, really need that.
Any other question? If not, let's thank Nader again.